acceleration in terms of velocity. All right, let's do an example in component form. If you remember my previous example, I had a dog that was near a rock and he walked to a tree. Let's analyze his motion while he was walking towards the tree. He starts to slow down as he gets to the tree because he wants to sit now next to the tree. So his velocity goes from an initial velocity of negative 1.5 meters per second x hat plus 0.5 meters per second y hat to 0 in a span of 0.5 seconds. So what they're telling me here is that v final is equal to 0, and I can write it as 0x hat plus 0y hat, just to be really clear that his final velocity is 0 everywhere. And the time span, or delta t, is 0.5 seconds. All right, so first thing that they want us to do is draw vi, that initial velocity vector, using this coordinate system where x hat points to the right and y hat points up. All right, so I'm going to rewrite my initial velocity vector in component form over here just to show you guys how I would do this. All right, so vi is the sum of negative 1.5 meters per second times x hat plus 0.5 meters per second times y hat. So this component right here, this is the vector component in the x direction, negative 1.5 times x hat. If x hat points to the right, then that means negative 1.5 points to the left with a length of 1.5 meters per second. So the length of that vector, 1.5, and the direction is to the left. All right, and now I'm going to add 0.5 times y hat. Y hat points up, so 0.5 is a vector that has a length of 0.5. Try to make that a little bit smaller. And it has the same direction as y hat, which is up. So those are the two vector components that make up vi. And so vi is the sum of those two. That's why I drew them tail to tail. And so vi is the resultant of those two vector components. And so that's how I would draw vi, is it's going to the left and up. It's going more to the left than it is up. I tried to draw it to scale, but obviously it's not perfect. But that is the general direction of vector vi. All right, so that's step number 1 done. All right, now let's try to express his average acceleration vector during this time interval in component form. And then we want to draw it as well. So if you recall our expression, the average acceleration is v final minus v initial divided by delta t. I already have vi in component form. Vf is just 0, and delta t is 0.5 seconds. So let's plug all of this stuff in. And so I get that acceleration average is negative times negative 1.5, so or 0 minus negative 1.5, so that is positive 1.5 meters per second x hat, and then 0 minus 0.5, so that one's going to get a negative 0.5 meters per second y hat. All of that is being divided by 0.5 seconds. So 1.5 divided by 0.5 is 3 meters per second squared, because it was meters per second divided by seconds, x hat, minus 0.5 divided by 0.5 is 1 meters per second squared, y hat. So here is my average acceleration vector in component form, and now they told us to draw this vector. So let's use our coordinate system. X hats point to the right, and this vector has a x component with a length of 3 and in the same direction as x hat. So 3 meters per second squared to the right. And to that, I am going to add negative 1 meter per second squared y hat. Y hat points up, so negative 0.5, or sorry, negative 1 meter per second squared points down. So I'm adding these two vectors together, which is why I've drawn them tip to tail. And now average acceleration is the sum of these two, so it is the resultant. So there is my average acceleration vector. It is pointing down and to the right. So notice that it points almost in the exact opposite direction as the velocity vector. It's something interesting that you're going to probably explore a lot later in your physics classes, but just food for thought. Just kind of think about the general directions of these two things. The dog was slowing down, and the average acceleration vector was in the opposite direction as the velocity vector. All right, and then this last part of it says to calculate the norm of the average acceleration vector while he was slowing down and the smallest angle it makes with x hat drawn on its tail. All right, so to do this one, I'm gonna go to another page. I'm gonna recopy my average acceleration vector in component form. And I wanna find the norm. And the smallest angle it makes with x hat. So that angle is also known as alpha. When you're looking at our vectors drawn in component or written in component form, alpha is the angle that it makes with x hat when it's drawn on its tail. So really what we're looking for is alpha. Let's first calculate the norm. The norm of this vector is going to be the square root of the vector dotted with itself. All right, I'm going to use my pre-approved shortcuts and nothing more than that. So just be careful, make sure you're still showing your work on these things. I am going to pull all these meters per second squared out so I don't have to keep rewriting all the units. Just remember everything had units of meters per second squared. So those two inner terms, I know we're going to go to 0 because x hat dot y hat is 0, x hat dot x hat is 1. And so I get the square root of 10, which is about 3.16. And again, everything had units of meters per second squared. All right. If you remember, our vector looked something like that. And we are trying to figure out the angle that this vector makes with x hat. We're trying to figure out that angle right there. If you recall in our generic description of a vector using that, we know that a vector written in component form is the norm of the vector times the cosine of alpha times x hat. So if I want to extract angle alpha, what I can do is I can dot my vector with that unit vector. And what I get is the norm of my vector, which I just calculated, times cosine alpha. That's kind of a definition. It's given on your equation sheets. You guys have used this over and over again. At this point, I can just kind of plug in my answers, all my stuff together so far. So this is my vector written in component form. I'm going to dot that with x hat. That is equal to the norm of my vector, which I just calculated, times cosine alpha. All right, when I do this dot product, the only thing that remains is the 3 meters per second squared. X hat dot x hat is the number 1. Y hat dot x hat is 0, so that term goes away. All right, and so in the end, I can just extract that alpha is going to be the inverse cosine of 3 over 3.16, which I believe is about 18.3 degrees. So that is that angle right there, angle alpha. All right, so I was just using a lot of the principles of vector math that you already know based on our previous work in modules B and C, just kind of applying it to acceleration vectors, but there's nothing special about an acceleration vector. It's just a vector. So you can use all your things that you've already learned about vectors and apply them to the context of acceleration vectors. All right, the last thing